The BDR will become the DR if the DR fails. Designated routers are chosen on a per segment basis. So in this example, on this Ethernet segment, R2 may be chosen as the designated router. But on this segment between R4 and R7, R4 may be chosen as the designated router. On a per physical segment basis, a designated router is chosen. So just because R4 is not a designated router on this segment does not mean that R4 is not a designated router on this segment. Every Ethernet segment requires the election and maintenance of a designated router. So from an update point of view, if this link goes down, R1 is updating its designated router using this multicast address 224.0.0.6. R2, the designated router, updates all of its neighbors on that segment. So R3, R6, R5, and R4 get the update about the change. R4 then floods that update to R7. R7 will then flood that update to any neighbors that it may have, not shown in this diagram. The same with R5, R6, R3, and so forth. The update will be flooded throughout the topology, just as in this example where R4 received the update from R2 and then sends it to R7. So just to sum up, designated routers, or DRs, are elected firstly based on the highest priority. The range is from 0 to 255. The default value is 1. 0 disables the ability for this router to become a designated router or backup designated router. If the priorities are the same, the router with the highest router ID will become the designated router. It's important to realize that preemption doesn't exist with designated routers. So in this example, if the priority of router 2 was set to 10 and the priority of router 5 was set to 5, and an election took place, R2 would become the designated router. However, if R2 went down, router 5 would become the designated router. And for instance, R3 would become the backup designated router. Let's assume that the priorities of the other routers are set to 1, but router 3 has the highest router ID, so router 3 becomes the designated router. When R2 comes back again, it will not become a designated router or backup designated router. In other words, it's not preemptive. Because R5 is already the designated router and R3 is the backup designated router, R2 will just accept that fact and will become known as a DR other or drother, depending which term you prefer. It will not try and preempt another election and try and become the designated router. All other routers, including R2, will become DR others in a topology like this. Let's talk about the shortest path first algorithm, or SPF algorithm. The SPF algorithm places each router at the root of a tree and calculates the shortest path to each node using the Dijkstra's algorithm, based on the cumulative cost that is required to reach that destination. So as an example, if router 1 wants to get to a network behind router 2, it's going to determine the best route based on the cost, which uses a formula 10 to the 8 divided by bandwidth. So as an example, this is a T1 link. Router 1 wants to send traffic to router 2. Will it take this T1 link, or will it use the path via router 3 using a 10 meg and 10 meg link? Now RIP using hop count would send the traffic directly to R2. But what would ospf do? ospf by default uses a reference bandwidth of 10 to the 8. You can change this, and you need to when you've got gig and 10 gig links. ospf has been around for many years, and in the early days there were no speeds such as gig, 10 gig, and so forth. So today, if you've got gig and 10 gig links, you're going to want to change this reference bandwidth. But for now, let's assume that we're using the default, so the cost of a link is 10 to the 8 divided by the bandwidth in bits per second. Now 1 kilobits per second equals 1000 bits per second. 1 megabits per second is 1 million bits per second. 10 megabits per second is 10 million bits per second. So the cost of a 10 megabits per second link is 10 to the 8 divided by 10 million, which gives you a cost of 10. Using the same formula for a T1 link, so for this link between R1 and R2, the cost is 10 to the 8 divided by 1544 000, which gives you a cost of 64. So the cost using this link would be 64. The cost, if the traffic was sent via R2, would be as follows: 10 to the 8 divided by 10 million, which is 10, but there are two links of 10 meg, so the total cost is 20. So the cost via the T1 is 64, but the cost via the 10 meg links is 20, so OSPF is going to choose the link via R2 to send traffic to R3, because the cost is lower based on this formula 10 to the 8 divided by bandwidth. So the default formula used for costing is 10 to the 8 divided by bandwidth. Now you can change the reference bandwidth by using this command within the OSPF process, order cost reference bandwidth, and then specifying a value in megabits per second. The default is 100, in other words the reference bandwidth is 100 megabits per second. 100 megabits per second has a cost in OSPF of 1. If you change this to 1000 as an example, a gigabit link would be seen as the reference bandwidth. Or if you change it to 100,000, a 100 gig link would be used as the reference bandwidth. You need to do this command on all routers where you have interfaces with bandwidths greater than fast Ethernet. You can also change the cost on an interface. So rather than OSPF calculating the cost of the link based on the bandwidth, you can set the OSPF cost by typing the command IP OSPF cost and then specifying a value. It's very important that the bandwidth statements on your router interfaces be configured correctly, because that's what OSPF deems the speed of the link to be. EIGRP does the same thing. It uses bandwidth as part of the calculation when working out the shortest route to a destination.